Okay, well, thanks very much, and welcome everyone. As Corey mentioned, my name is Craig Simmons. I'm a professor in mechanical and industrial engineering on the mechanical side. I also have a cross appointment to the Institute of Biomaterials and Biomedical Engineering. I do work in the areas of biomechanics and kind of the interface of biomedical engineering and mechanical engineering. What I'm going to talk to you today about is the mechanical engineering program, and what is mechanical engineering, is that maybe the option for you to take. Tell you a little bit about our department and the students in our department, and then I'll spend the bulk of my time telling you about the technical streams you can do within mechanical engineering, because those define a lot of kind of the types of work that people end up doing. I'll tell you about all the technical streams. I'll tell you a little bit more about the one technical stream that I'm involved in, which is the biomedical option, and then I'll tell you a little bit about the curriculum and have lots of time for questions and answers. So first off, what is mechanical engineering? And really, we like to think of a mechanical engineer's work as involving kind of anything that moves. So I don't know if you've heard the civil lecture yet, but the civils, they think of things that don't move. We think of things that do move. And mechanical engineers design, manufacture, and operate those systems that really extend our physical abilities and allow us to do things with machines that we couldn't do otherwise. And I think that's a nice broad definition that captures a lot of what you're going to hear about today. And so you can imagine that mechanical engineers contribute to a wide range of industries and a wide range of advances because they're really touching any mechanical system, anything that has these moving parts. And so mechanical engineers tend to be people who like physics and math. We do, a lot of the movement is all physics-based. I think you're all probably in an MIE 100 right now, and that's kind of a core mechanical engineering type course. That's basically a physics course. So if you like that sort of stuff and the math that goes along with it, that's a good indication you like mechanical engineering. And I guess thinking, not on the slide, but just thinking about how things work. If you like to think about how things tinker, if you build Lego when you're growing up, or you like to pull things apart, just thinking about how things work and can you make new things. I think designing new things is a big feature of mechanical engineering. And then do you have interest in some of the streams that we offer, which have a mechanical focus? Bioengineering, aerospace, robotics, all of these have strong mechanics components I'll tell you about. And then even things that you may not think of as mechanical engineering, but alternative fuels and energy. Also a big role for mechanical engineers in those fields in making new fuel cells or making new turbines for wind energy or other alternative sources of energy. Okay, so again, you can see broad range of applications. So our department is quite large. We're one of the larger departments in engineering. We have 57 faculty members that you can see split by different levels, full associate and assistant professors, and a lot of administrative and technical support staff, 32. A lot of that staff is actually in place to support the labs that we run. So we have a really nice suite of labs and lab spaces that are supported by dedicated technical staff. And MIE has put a lot of investment into building up those labs and building up the technical support staff to really make that a fantastic learning experience. So not only do you get the lecture material, but you get to get your hands wet and dirty in the lab, really getting an appreciation of the theoretical material you learn in lecture, seeing it applied in real-world circumstances. So we have a large number of students, 1,300 students total. And you can see that they're split. We have both Indy and mech in our department, and we have more mechs than Indy, but kind of maintain that ratio throughout. And this is maybe a little out of date, but about, a lot of Track 1 students end up joining MIE programs. I think this is from 2 years ago. So it is quite a popular option for Track 1 students. And I think there's good reason for that. There's good job opportunities. We'll see some examples of that throughout the presentation. Interesting courses, wide variety of flexibility in the sorts of things you do. Okay, so that's a broad overview of the department. Let's talk a little bit more about the nitty-gritty, the technical stream. So in third and fourth year, you enroll in 2 technical streams, and this defines where some of your technical electives will be taken. And these are the technical streams we offer in the department. And these really reflect 2 things. They reflect the specialty of the faculty, and so our faculty members are all experts in these areas. And they also reflect kind of hot areas where there's a lot of demand, where there's a lot of jobs, and where there's a lot of opportunity to contribute. And so you see them listed here, and I'll just go through each of them in order. So energy and the environment. Clearly, super important problem right now facing that we all face is sustainability and how we're going to find alternative sources of energy, or how we're going to even use the energy sources we have now more efficiently. And so some of the courses you take are related to kind of gas and power cycles for engines. So this is things, engines that are being used now, but looking towards improving those. Refrigeration and cooling, steam power plants, very traditional kind of energy. And then in 4th year, you start thinking about more alternative types of energy sources. So solar, wind, wave, and so on. And how can mechanical engineers contribute to advances in these cutting edge fields that are clearly the way of the future? And so lots of opportunity there. Really, what you're going to be learning is tools to model these energy systems and design energy systems. So apply that knowledge and that modeling skills in order to design new energy systems. And again, we have lots of expertise in the department, in fuel cells, in alternative energy sources, and in modeling and combustion. So really broad expertise there. And then we have many graduates who've worked in the program. This is one of them, Eleanor Lee. She's available she's indicated she's willing to connect with you through the Connect program, or talk to you through the Connect program. So if you're not already signed up through Connect, this is a fantastic platform for you to connect with current students and alumni. And I think the alumni is the key. You can immediately establish a network of U of T alumni working in fields of your interest. Whether you go into MEC or not, it's still, I think, a fantastic opportunity. I've signed up, and I'm always getting these notices from interesting people, and it really has expanded my network. So I'd encourage you to sign up, and then if you're interested in this sort of thing, for example, someone like Eleanor, who works for Ontario Power Generation doing nuclear engineering, I think she did her PY there, maybe? Is that, Shannon, do you know?
Yeah.
Because it says, yeah, because she's now, yeah, so now she's working, yeah.
If you're on her full profile, you can actually see more detail down below. I just took a snapshot
Yeah.
to be able to fit on the slide.
Yeah, so you can see she worked on the solar team, so building a car that uses alternative energy. She now works as a mechanical engineer at this company, had some PEY experience, and graduated in 2015. So an example of a grad from our program working in the energy field, did energy stuff well here at U of T, and is now again on the Connect program. Another stream that's really hot right now is manufacturing. Ontario is manufacturing is kind of a core activity within economic activity within the province. A lot of companies manufacture within the province, and manufacturing, and so mechanical engineers contribute to that substantially. So manufacturing stream will allow you to design, to learn tools to design products, for making and assembling products, for designing manufacturing processes, and for doing the statistics of manufacturing. How do you know that your manufacturing process is going to reliably produce a part that doesn't fail? And so you learn courses on quality control. What's involved in making sure that manufactured parts meet quality assurances. Automated manufacturing, computer-controlled manufacturing, computer-controlled machining. All these are kind of core skills and core knowledge you'll gain that apply to the manufacturing field. This, as I mentioned, super hot. Lots of jobs in manufacturing across a wide range of industries. They're not specific to a single industry, but you can think of automotive as one big one, electronics, and so on. Manufacturing was identified just recently by the federal government as part of a super cluster, and centered in Toronto. So there'll be a lot of activity going on within manufacturing, advanced manufacturing here in Toronto. We have an institute for manufacturing that's led by Hani Naguib, one of our faculty members in mechanical engineering. So this is a really, it's always been a hot area. It's a super hot area at the moment, and I think there's going to be this explosion in opportunities within manufacturing as a result of the investment of the government, particularly locally, regionally within the Toronto area. And MIE is taking the lead on a lot of that. So if you go on Connect, you can connect with many people working in this area. This is Ellen Chan. She's one example of a graduate working in a manufacturing. She works for Stryker. Stryker is a medical device company. She's a mechanical engineer, and you can see is involved in process development, so that not only making the products, but making the processes that allow you to make the products. And you can see she got her master's degree in MIE, did PEY at MIE, worked as a research engineer at Stryker for quite a while now, and she's also willing to help and is available to contact if you want to talk to her.
Ellen actually did her undergrad in materials.
Oh,
and,
okay.
and really enjoyed it here at U of T, and then switched over. So you're not really limited to the fields depending on what you go into, but it's a neat example of the different paths you can take.
Right, right. Our third stream we offer is mechatronics. This is at the interface of mechanical engineering and electrical engineering. This is really, you can think of this almost as robotics. That's how many of us think of it. You're integrating electrical and mechanical systems. So you'll learn both electronics, digital analog course, circuit design and analysis. That's the electronics side. You learn control systems programming and design of controllers. So you can imagine for robots, I don't know if you saw that video from Boston, what was the company's name? It's like the walking robot that goes up to the door. Did you see that? I was on Reddit and I saw it on Reddit. It's Boston Dynamics, thanks, yeah. So they got the robot that walks up to the door, looks at the door, can't open the door, calls his buddy robot, come over and open the door. So that's the sort of control, like how do you get the robot to reach out and grab a door handle, turn the door handle, and not break it, for example. So control theory, important in all of these systems. And so we have, again, a lot of expertise within the department in mechatronics, this interface between electrical engineering and mechanical engineering, a lot of expertise in robotics. We are the lead of the U of T's Institute of Robotics, led by Goldie Najat. She's an MIE faculty member. She makes robots that both do things like search and rescue type stuff, but also robots that interact with people. So they have robots that go into a seniors' home and play bingo with seniors and interact as sort of a social level. So lots of really interesting things you can do here. Grad that's from that program, grad from our program who's working in that area is Brendan Sline. He's working as a design manager at Toronto Community Housing actually now, but is working this field and again is available for connecting. He graduated from the mechatronics option a long time ago, and you can see he's had this really interesting career where he's progressed through multiple companies. So I think that's the other feature, that a lot of our mechanical engineering grads aren't pigeonholed into a certain industry or a certain type of job. They get the translatable skills that allow them to do this sort of moving up and through to project management level and senior project management level quite rapidly through the ranks. Solid mechanics is kind of a core component of mechanical engineering. This is learning tools to model using computer-aided design, so modeling parts, conducting failure analysis. Will parts break or crack? And you could do that both experimentally and using computational modeling, finite element analysis. And all this is also related to manufacturing. So in this stream, again, you're getting this core expertise in solid mechanics that can be applied to a wide range of fields. Here, for example, is a machine part on an engine. It's a stress analysis that's been done here, and you can see there's some high stresses here and low stresses here. And this would allow you to figure out whether this part would fail under normal operation. And you could design then based on these sorts of analyses. So you'll take courses that allow you to do this computer modeling of stresses. You'll take courses on how to do computer-aided design. And then in fourth year, you have electives, but you also have the option of replacing a term project with machining and welding courses that are offered through George Brown. So these are really outstanding courses. I've had a few students take these courses, and they gain some really outstanding skills that they can then use in the future, either in a job or in another project or in graduate school. And the training you get through these courses is really top-notch. It's well beyond what we can offer here at the university. George Brown College is training machinists, and this is the side, you get to take the courses alongside with them. So this is a really good opportunity to get hands-on training of a translatable skill again. So example of a graduate from a program who's working in this area is Jess Dand. You can see he's now a management consultant. So again, this idea that he did the manufacturing option, but has been able to, and did PY in that area, but now is working in management and management consulting, again, showing the ability to move between fields. Okay, and then the final stream I want to talk about is bioengineering. This is the stream I work in, and so I'm going to spend a little bit more time telling you about some specific problems that demonstrate how mechanical engineers can contribute to bioengineering. In the bioengineering stream, we're really interested in how to model and control human physiological systems, so the body. The courses there include a course in physiological control systems. So if you think about it, how does your body regulate temperature? Right, your core temperature doesn't really vary from 37 degrees, whether you're in really hot weather or really cool weather. So how does the body keep that control so finely tuned despite all these external forces that are really trying to push your body cold or hot? So you talk about control systems like that. And then in fourth year, there's several courses that allow you to apply mechanical engineering principles to model and solve problems in fluids, like related to fluids, heat, mass transfer, solid mechanics, and so on, related to things like blood flow in an artificial blood vessel. So applying mechanical engineering principles to study and analyze actual human tissues and organs. So here's an example of a problem I work in, or an area I work in, and how, as a mechanical engineer, we've been making some, I think, important contributions to the area. So the problem is that we study heart valve disease. So here's a normal heart valve. This is the heart valve called the aortic heart valve. And this is a pig valve, actually, but you can see the leaflets are very thin, they're very pliable, they're opening fully, no problems with this valve. On the right is a diseased human valve. And you can see right away that these leaflets that make up the valve, they're thickened, they're lumpy, they're discolored, there's actually bone in here and scar tissue. And you can see it doesn't really open fully, right? This part never opens back here. And what this means is that the hole that the blood has to go out of is much smaller than it would be in the normal case. And so the heart now has a high resistance, a very small area to pump blood through, and has to pump a lot harder. And so someone who has disease like this, if it gets advanced, they'll probably die within 2 years because their heart just can't keep up with the demands that are, the pressures that it's required to get blood out of this small hole. Okay? And so this is the problem. And right now there's no solution. There's no drug you can take to prevent or reverse this process. So we're really interested in understanding why does this occur and what can we do to prevent it. And so, you know, all these bioengineering problems, you've got to know a little bit about the biology. You don't have to do biology, so you don't have to memorize biology, things like that, but you have to understand what systems you're trying to engineer. So this is the heart, a diagram of the heart, and you see it's got 4 chambers, and the blood moves from the atria, these top chambers, to the ventricles, and then it gets pumped out of the heart to the rest of the body. So the red one is the oxygenated blood. That's going to go through this valve here, and it's going to feed everywhere in your body except your lungs. The blood that comes out here is deoxygenated. It's going to go to the lungs where it gets oxygenated and comes back through here. So the valve we study is this one right here, the aortic valve. It's the valve between the left ventricle, the main pumping chamber, and the aorta, the main blood vessel that's carrying blood to the rest of your body. And it's a very simple structure. It's just 3 flaps of tissue, and it just, when the heart pumps, contracts, the pressure in the heart increases, and it forces blood through the heart valve, and the heart valve snaps open. And then when the heart relaxes and the blood falls back onto the valve, it snaps shut. And so it's just a check valve. That's all it does. It just prevents blood from flowing backwards into the heart, keeps blood moving in one direction. So really simple function, but critical. If you don't have it or it becomes diseased, as I said, you can die within a couple years. Okay? And so this is the valve that gets diseased, and really, I'll tell you about what the solutions are now. So when this was first recognized as a problem and people said, well, can we maybe replace this valve? Right? Can mechanical engineers help replace this valve? And so the first replacement valves were a collaboration between a physician and a mechanical engineer. And what they came up with was a really clever design. It was a ball in a cage. And so what you can imagine is the bottom of the cage down here would be the left ventricle where the blood's coming from, and it would flow up here, and as it flowed up here, it would push the ball to the top of the cage, flow around the ball, and then when the heart relaxed, the ball would drop back down and seal off the valve, right? Really clever. The first versions of this actually didn't have this fabric on it, and so what the patients would hear, they'd hear click, 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 as the ball hit the cage, right? Metal ball hitting metal cage. And it drove them nuts, right? So their heart was working fine, but they couldn't stand the constant clicking. So first design, mechanical engineer not really thinking about the bio implications, right? Or the ergonomics, the interaction with the humans. The first thing they do is put fabric on here to muffle the sound. Okay, so these work great, work quite well. And future versions then went away from this. The problem with these as well is that, again, a mechanical engineering problem, the constant pounding of the ball on the cage caused the struts to fail, actually. Right? You can imagine you're hammering on the pressures here are very high. So you're just constantly hammering on these struts, and they weren't engineered to handle that loading. These would fail, and then you'd have this metal ball flying around your blood vessels, and clearly that's not compatible with life, right? So those people died. So this, so this is important stuff, right? You're making life and death design decisions here. So now most people use this. Most people use this as an artificial valve. It's two flaps, and they do this. They tilt. Okay, so when the heart contracts, they tilt up like this, blood rushes out. When the heart relaxes, they tilt back and seal it off. Works great. Okay, works really well. Plastic, don't have the clicking, doesn't fail. It's been designed. People now recognize that it has to be designed that way, so they're very well designed. The only problem with them is that these flaps get in the way of the blood flow. And this is where having some knowledge of the bioengineering is important. This maybe doesn't, if this is just water rushing by, no big deal. But this blood contains a bunch of blood cells. And those red blood cells, when they feel these forces of having these obstructions in the way, they get damaged. And it causes them to think that there's a wound, and they start clotting. Okay? So the problem with these synthetic or mechanical valves is they cause the blood damage, and they cause clotting as a result. And so again, the first experiences were clots being thrown off. Those cause strokes and heart attacks. So now patients who are on these are still used, and they're very common. Patients on these have to take blood thinners. So for the rest of their life, they're on blood thinners to prevent their blood from clotting. For an elderly person that's not very active and is not really prone to bumps and bruises and so on, that's probably okay. But for a younger person, say a baby born with a defective heart valve, or a young person who gets valve disease early because of a congenital defect, it's not a great solution, right? You can't be as active, you're more prone to bleeding. If you do get cut, there's nothing to clot, you bleed out. So this has been okay for certain patients, not for everybody. And so mechanical engineers started thinking about, well, what's the real valve look like, and can we design something that looks like a real valve? So this is what the real valve looks like. I showed it to you earlier. It's got these three leaflets that come together in sort of this peace sign. One of my former students thought it looked like a Mercedes-Benz symbol. And he thought he was going to get rich from doing heart valve research, but now he's a professor in mechanical engineering, so it didn't work out that well. He's certainly not driving a Mercedes. But it looks like that, right? It's these three leaflets that come together. And so now what the current version of replacement valves is they're called bioprosthetic valves. So they really mimic the actual structure of a real valve. In this case, they're made out of pig tissue or cow tissue that the cells have been pulled out. It's been treated with a chemical to make it durable. And then just by sort of sewing it together, you can get something that looks exactly like a heart valve. And you can see it opens fully. So there's no longer problems with clotting in these systems, right? Because there's nothing obstructing the blood flow. The problem with these systems, though, is shown by this finite element analysis, this computer model of the stresses. You can see the hot spots, right? These are high strains that are generated in the tissue when it opens. Those high strain regions fail. They break down over time. And so eventually this valve it'll become calcified, actually. So it breaks down, you start getting calcium buildup, and it stiffens and has to be replaced. So patients with these don't take blood thinners. so they're good for younger patients, but still not good for babies, right? They don't grow, so babies still are a problem. But for younger patients, they're better, no blood thinners, but they'll have to be replaced. They have a short lifetime, 10, maybe 15 years if you're lucky. Okay? So a better solution, but still not a great solution. And so this is where we've come in, and we're starting to think, can we improve upon this even? And can we do something to help a baby? Right? A baby is born with a congenital heart defect. About 1 in 100 babies will have a defect in their heart when they're born. Can we do something to give them a valve or repair their valve early in life that will last them a lifetime? And so what we've done is what we're doing is we're looking at real hearts, like this one here. Okay, so this is a heart. Okay, probably not what you expect when you're coming to a mechanical engineering thing. Okay, so here's a heart. It's dripping. Okay, so this is from a student who went into the ECE from track 1 last year. Okay. Just putting that out there for you. So no, really, it's a pig heart. Okay, so this is a pig heart from a pig. It's very much like a human heart. Okay, and so we study this because this is same size as human, same biology, very similar biology to a human. So what we're doing is we're studying the biology of this heart valve. So now in my lab, not only do we have mechanical engineers, we have biologists. And we're trying to understand, how does the heart grow? How does it keep healthy? How does it maintain its not become diseased or fibrotic or scarred or calcified? And so we're studying that and how do mechanical forces influence that. All that knowledge of what we're gaining from studying the mechanics of real hearts and the biology of real hearts, we're now applying to engineer hearts and living heart valve tissue. So the problem we're studying is that babies born with a congenital heart disease have a defective valve. And we study, in this case, a pulmonary valve, the one that feeds the lungs. And so when the baby's born, the idea is that the surgeon knows before the baby's born that the baby has this defect. So at birth, we know that something has to happen. They have about 6 months where they do okay before typically surgeons will replace the valve around 6 months if they're going to replace it. 6 months of age. Right now what they use is fabrics like Gore-Tex. So if you've got a jacket like mine, that's the type of materials they're using right now. Clearly those aren't good, right? They don't grow with the baby, they end up scarring up, they end up having to be replaced. So the surgeons really don't have a good solution. In some cases, they won't even repair the valve. They'll let the baby grow up till a teen with a defective valve. The risk there is the baby's heart can start failing or they can actually die suddenly. So it's a trade-off. Do you repair it early and then have to do a lifetime of operations because you don't have a good material to work with? Or do you take a chance until they get to a teen and then put in one of those bioprosthetic valves? So not great decision either way. So what if we could give the baby a living heart valve tissue? What if we could give the surgeon a piece of tissue that's alive and that will grow with the baby as the baby grows? That's our dream. So they know the baby's going to be born with a defect. We take the umbilical cord at birth, which is normally thrown away, and there's actually a bunch of stem cells in that umbilical cord. And these stem cells are really good at making tissue like heart valve tissue. So we put those stem cells and we put them on a biomaterial, which is a kind of a scaffold or a fabric, and they go on there and they start producing tissue that's like valve tissue. And this is where what we've learned from real heart valves comes in. We know if we can actually stretch the tissue, if we exercise it, we can actually make the tissue grow a little better. It becomes stronger. It becomes more like a valve tissue. It becomes aligned. It thickens up a little bit. And this is important because the tissue at this stage isn't fully formed, but after we do this exercising, kind of like you go to the gym and lift weights and your muscles get bigger, we can do the same thing with these tissues in the lab. So what we end up with is a sheet of tissue that's like a valve. And now we can hand this off to the surgeon, and they can do all sorts of cool stuff with it. They can do origami to actually make a 3-leaflet valve. That's what it's called. It's called valve origami. Or they can take the tissue itself and repair the valve. And so the goal here is that ultimately we'll end up with a normal heart, with a living heart valve that will grow with the child and repair itself as the child's heart, as the child puts new demands on its heart. So a kind of extreme example, I think, of where mechanical engineering comes in. But what we're doing is we're We're using mechanical stimulation and building bioreactors that do this stretching. So this is all mechanical design. We have to understand the mechanical properties of the tissue to make sure we're matching the tissue we're trying to replace. We have to understand the mechanical properties of the scaffolds we're building and their alignment and their structure. All this is design and manufacturing, and everything's moving, right? And that's what I talked about earlier. Everything's flapping in the fluid, and so we have to understand what are the forces being exerted on it in the body, so we can design for that. So kind of, I think, an interesting example of how mechanical engineers have contributed to various stages of heart valve replacements and the next generation. So other courses you could take within this stream are shown here: surgical and dental implant design, physiological control systems I mentioned earlier, and then I teach biomechanics, MIE 439, and Professor Yu teaches transport. So courses on biosolids and biofluids. We have lots of grads working in this area. Danica's one who took my course several years ago now. She works for St. Jude, one of the world's biggest medical device companies. She's the territory manager for the cardiovascular division. She also did PEY. She went on to do a master's degree here in biomedical engineering and clinical engineering, and has really done really well, kind of, again, working up the ladder at St. Jude. And again, she's on Connect and willing to connect with you. So, curriculum. Year 2 of mechanical engineering, the one you'd go into next year, really provides you with foundational courses. These are really just to give you the foundation and as a stepping stone to get into the streams. So you take engineering analysis, kind of math, probability and statistics. You do design throughout every term of the curriculum, so you'll take a course in design. Material science, Shannon mentioned earlier that some of our grads, or our graduate student in that one case went through materials, but you do get material science courses within our major, and then complementary studies. And then in winter, you get, again, you finish off your math base, do thermodynamics, mechanics of solids, manufacturing engineering, core topics that will be important to any stream you go into. And then from third and fourth year, or in third and fourth year, that's when you start specializing. You pick 2 of the technical streams, and that will define where your electives are. In fourth year, you do capstone design. It's all client-driven, really fantastic projects coming out of that. And you have the option to do a thesis as well. And again, there's a design theme that kind of percolates through the entire curriculum. Okay, so if you want to know more, this is our website. Shannon is willing to, if you have questions, you could email her and meet with her to discuss. And we have time for questions now. I'm happy to take them. Thank you. Any questions? Yeah, so I don't teach those courses, so I don't know specifically. I know a lot of the students will use SolidWorks. They'll use ANSYS for the finite element side of things. AutoCAD is also used quite a bit. Kind of the standard, those are the standard big 3 that I'm familiar with. They're using a lot of companies as well. There may be other ones that I'm not aware of, but certainly the students I worked with have all had those experiences. Yeah, like, almost everybody in mechanical does great SolidWorks work. It's pretty amazing. Like, because that didn't exist when I came through, and I'm always blown away by the models they can make, because it helps with the design process, right? It's like a virtual design, and so you can see how parts fit together. You can produce engineering drawings immediately from the SolidWorks. You can get a sense of how things will move. Really powerful stuff, and again, the sort of tool that you can use for any field, right? So I think it's really beneficial. Yeah.
Is MIE 100 like an accurate representation of what we've learned in MEC?
So I think MIE 100 is known as like one of the tougher courses, right, in first year. It depends on what stream you go into, I would say. So if you go into kind of the manufacturing where so MIE 100 feeds very well into understanding how machines work, right? When there's things moving around a lot, so you've got levers moving and things rotating. So there are courses in machine design that feed directly from MIE 100. So it'd be greater representation in that case. My biomechanics course, we do a little bit about walking, right, or running. And that's dynamics. There's accelerations, there's F equals ma. If I want to know what are the forces on my knee, I have to do F equals ma and m equals I alpha, right? And I have to figure out what are the accelerations, linear and angular. So certain topics within my course build on dynamics. If, however, you go into something like energy, you're probably doing more fluid mechanics and heat and mass transfer, then MIE 100 becomes less relevant. I think the idea, though, that you're doing physics and math is consistent with a lot of the technical electives within MIE, within mechanical, yeah. But the specifics of MIE 100, I think, only apply to a certain subset of streams, yeah.
There's not a lot from MIE 100 in the industrial.
No, yeah, not at all, yeah, that's true.
I'm gonna remind you guys that a few weeks ago.
Yeah. Other questions? Yeah.
In the prosthetics field, do you see an initiative in the industry to replace parts of your body that don't need replacing?
To like augment your abilities kind of thing? There's a whole DIY movement like that, right? Yeah. We don't see that, to be honest, but certainly like exoskeleton type stuff for military applications and so on is to, can I lift a car by using an exoskeleton when I couldn't do it on my own? Certainly there is a lot of effort in that area. I don't think we see as much of it in Canada because a lot of that's military funded, so a lot of that activity in the US. But all the prosthetics work and rehab work that goes on, so one of the Toronto's strengths is in rehabilitation engineering in terms of biomedical engineering. We have the Toronto Rehab Institute, which is the #1 rehab institute in the world in terms of research. And they do a lot of assistive devices, rehabilitation engineering, prosthetics. Jan Andrzejczyk has a company called Legworks where they've made prosthetic knees and legs for third world countries. They're kind of a superstar company in that area. So there's a ton of work in that area. It's being applied, though, for people that need it, not for people who want to do more than they could otherwise in terms of augmentation. But the approaches are all the same, right? So there's no reason you couldn't do that with those technologies. Yeah. It's a hot area, though, particularly man-machine interface or human-machine interface. Can you now run these prosthetics by thinking about it, right? And that interface between the body and the machine. Huge activity in that area. And can you use electrical stimulation to control the body, right, is the other side of that. Milos Popovic is making people walk, allowing people to walk through electrical stimulation now. So that interface he's a mechanical engineer. That's all under mechanical engineering. Yeah. Anything else?
Well, I'll just ask, I know we hear this often, is the students asking the difference between electrical and mechanical for something like mechatronics?
Yeah.
I don't know if that's a question we hear is wondering, but.
Question. I get that asked all the time.
Yeah, if nobody's asking it today, I know it does come up
Right,
often, that
right.
students are wondering.
I can give my perspective. So I don't work in that field directly, but I can give my perspective. So where I think the difference would lie is on the electrical side, probably more involved with the programming and the circuit design and the electrical analysis. On the mechanics side, I think it's more, it has aspects of that, of course. You can't have one without the other. But if you think about robotics, you got to take those electrical signals from your circuit and do something with them, right? And I think that's where the mechanical engineer comes in, is that they build the systems, design the systems that enable whatever the electronics is trying to do. So building the robot part, and then the control theory is part of that. So how do you control the movement for that Boston Dynamics thing where the robot opens the door? How do you control that movement and have the feedback so that it doesn't rip the doorknob off? So both the control and the implementation, the actual design and building of the hardware, I would say is but it's kind of a gray zone, right, between the two as well. Yeah, but I think a lot of mechanical engineers like to see things, and they like to be able to put their hands on things and see how things work. That's a little more difficult to do if you have a circuit. You don't see the electrons flying around. So a little bit different perspective.
Maybe a question for you and Shannon, but just in your experience or based on what you know about the courses,
Sure, the ones that, I know our undergraduate office deals with most are the kind of energy, environment type streams, and bio are quite popular. Engineering business, I think, is popular across all, engineering. We have a quite surprising number of mechanical engineering grads who do go on to pursue an MBA, and end up working in the business side of wherever maybe they started their career. If they started manufacturing, then they're gonna go look, maybe get an MBA and look at the business side of how to move forward with that.
Yeah, and project management, I think a lot of grads go into project
Project management
management, yeah.
I'm gonna send Corey an email to invite you guys all next week to a lunch and learn we're having with one of our mech grads who is a senior guy at H.H. Angus, which is a big engineering and consulting firm who they worked on things like the Sky Dome, or it's not called that anymore, but the CN Tower and the AGO and some really big buildings in Toronto. And he'll speak about how they had to engineer different challenges in those spaces. So that might be an interesting way to see, how mechanical engineering is impacting some big famous buildings that you might know about.
Great.
Yeah, sorry.
What kind of minors and what kind of classes would you take if you want to lean towards like a aerospace type? Because I know we're not specializing in aerospace.
Right, right. So there are courses, there are technical courses that would align with aerospace and kind of in the fluids realm, as well as the solid. So the solid mechanics stream has courses in structural analysis, things like that. They're important for aerodynamics and for aerospace. So that's there are definitely technical electives. I don't know if there's a minor that's really applicable.
Not a specific minor, but you'd probably be looking at the SolidWorks, the mechatronics to learn like the control system, and even some of the manufacturing stuff.
Yeah.
Depending on what type of aerospace work you want to go into, it really impacts the courses that you're going to take. So mechanical engineering is quite broad. It can be applied to a lot of different industries. So it's looking at the aerospace industry and what part of the aerospace industry you want to work in.
We have faculty who work on stress analysis on a wing, for example, right? So it's the solids aspect of aerospace. So in that case, it's clearly the manufacturing and the solid mechanics streams. But if you're interested more in the airflow aspects of it, then that may be then, even energy has courses in that area. So you kind of could pick and choose that way, yeah, depending, like for specific courses to fit specific streams. Sorry, yeah.
I was just wondering, what's the biggest difference between bioengineering with mechanical engineering versus biotechnology with chemical, in terms of like the application and what type of engineering?
Right, right. Good question. So bioengineering is really broad. So what the examples I gave you today were biomedical engineering, which tends to be bioengineering applied to human health and biology. So bioengineering also encompasses environment, food, kind of anything biological. So in chem, there's a lot of intersection between chemical engineering and bioengineering big in terms of environment, food, natural resources, things like that. There's a little bit also with human biology and medical systems and biomedical engineering in terms of materials. There's a bit of like synthesizing new materials that could be used to replace parts of the body, understanding how to grow a stem cell in a bioreactor to make lots of stem cells for a treatment. So bioprocess applied to human biology. So that's where I think the intersection between chem and bio comes in. Within mech, we don't do much bioengineering except the energy and the environment stuff, but that tends to be very energy focused and not like food or resources like they do in chem. So within mech, it's much more biomedical, I would say. And in that case, it's a lot of building devices, understanding the mechanics of the system, because if you want to replace something, you have to understand how it works, building diagnostic systems, 3D printing tissues, stuff like that. So I would say more device and product oriented, and more characterization of the mechanical environment, whereas the chem is more, on the biomedical side, is more materials and understanding the chemical environment, kind of, and bioreactors processes. Yeah. Yeah.
One more question. Yeah.
Okay, so if you're looking for a design which would thank our brain to treat the tough is
Yeah.
it
Yeah. So that's what I was mentioning earlier. There's these person machine interface type work. So that's going on both in electrical and mechanical and biomedical. So the bioengineering stream and the biomedical minor gives you access to those types of courses for sure. There's a neural systems course, for example, as part of the bio minor that you could take as part of the fit it into the stream. And then I would say mechatronics is the other side of that, because a lot of the control theory and the electrical systems, those are all used for these types of applications. So I think within Mac you could hit in those areas through a mechatronics and bioengineering combination. You could do it probably through electrical as well. I don't know what their streams are, but certainly through Mac you can head in that direction. Yeah. Physiological control systems, that MIE 331, it's all about that. It's how the body controls itself, but then how we could also influence control externally, right? So, yeah.
For those of you who are asking questions about the biomedical stuff, it's great because Craig is here and he can definitely answer those questions. We're also going to have someone in from the Institute for Biomedical and Biomaterials Engineering, so IBBME, later in the seminar. So they will come in and talk about their minors and courses and pathways into that field, and mechanical is definitely one of them. So those are great questions. It's good to know that there's interest here because we will be having them join us as well. One last round of applause for Craig and Sam.
Thank you.